Okay, let's unpack this. We are living in an era where industrial sensors, the silent, tireless observers embedded in every turbine, every compressor, every single hydraulic pump are generating just mountains of data.
It's an absolute flood.
It's completely overwhelming. But the real magic, the breakthrough that turns that mountain of noise into pure high-value actionable intelligence is knowing precisely when a component, say a bearing assembly or a critical valve, is going to fail.
Right.
And we're not talking about sometime soon. We need to know, down to the shift change or even the hour when that piece of machinery needs proactive intervention.
And that's exactly the deep dive our listener requested. They shared a stack of incredible sources detailing the mathematics underpinning modern prognostics and health management, or PHM. We're moving light years beyond basic threshold alerting.
Mm.
Today, our mission is to pull back the curtain on the advanced machine learning architectures from, simple, robust ensemble methods like random forests, all the way to the complexity of transformers and the speed of temporal convolutional networks.
We're going to show you, the listener, exactly which algorithm is custom-built to catch a sudden, novel pressure spike, that one fault the system has never seen, and which one is dedicated to predicting the slow, inevitable creep of degradation over months.
And most importantly, how all these specialized tools integrate into a single high-stakes, real-time pipeline.
Exactly.
The analogy we're using for the learner today is crucial. We are not just gazing into a crystal ball to see the future of machinery.
No, not at all.
We are examining the underlying physics and the sophisticated mathematics that explain why that crystal ball works. And we'll demonstrate why the math itself needs to shift dramatically depending on whether your goal is to, say, immediately detect a sudden breakdown or to forecast a slow death curve.
It's all about matching the perfect tool to the exact failure mode. Let's ground ourselves with a foundational tool in the supervised toolbox, random forest, or RF. My understanding is that when you have historical data that is well-labeled, meaning you know exactly what the vibration, temperature, and load looked like in the 72 hours before a pump failed, RF becomes this workhorse for classification.
You've hit the nail on the head. It's all about defining those equipment health states, like healthy, mild degradation, severe wear, or failure.
And its strength comes from its name, right? It's an ensemble.
Precisely. The strength of random forest comes from that ensemble learning method. It relies on strength in numbers. So instead of relying on one huge, complex decision tree that is, susceptible to a single noisy sensor reading, RF builds hundreds or even thousands of individual specialized decision trees.
And they all get a vote on the final outcome.
They all vote. And this ensemble robustness is absolutely essential in an industrial environment because, as you know, sensor data is notoriously noisy, redundant, and often includes missing values.
And the beauty of that whole approach lies in the introduction of deliberate randomization, doesn't it? How is that randomness injected mathematically to ensure the final model is so stable and resistant to overfitting on, say, one specific batch of noisy training data?
Okay, so there are two key steps for injecting that randomness, which is really the magic of the ensemble. First, we use something called bootstrapping.
Bootstrapping, okay.
So for each tree that's built, we randomly sample the training data with replacement. Now, what this means is that some historical data points might be used multiple times in training one specific tree, and others might be left out entirely.
So those are the out-of-bag samples I've read about.
Exactly, and those are really useful for internal testing. But the main point is, this process guarantees variance across the models.
So every single tree sees a slightly different, randomized version of the machine's history. It's like they each get a slightly different textbook to study from.
That's a great way to put it. And the second ingredient is even more interesting. At every single split point within a decision tree, the algorithm only considers a random subset of features.
A subset, so not the whole picture.
Not the whole picture. If you're collecting 50 different sensor features, vibration kurtosis, oil pressure, motor amperage, cooling loop temperature, you name it, a single node split might only be allowed to look at, say, 3 or 5 of those features to make its decision.
That prevents one single feature from just hijacking the entire model structure.
Right, I can imagine if rotational speed is the overwhelmingly dominant signal, restricting the feature pool ensures that other more subtle indicators, like the relationship between two specific temperature readings, get a chance to contribute.
Precisely. They get a chance to contribute across the entire forest. The final prediction, therefore, isn't based on one tree's biased or potentially noisy output. It's a stable consensus majority vote from hundreds of these specialized, slightly limited trees.
And that collective stability is why RF is so robust.
It is. Okay, so when those individual trees are deciding how to split the data, how do they determine the best possible point to make the cut? I remember seeing a concept in the sources related to purity.
That's the core mathematics of classification, and the concept is Gini impurity. Think of it this way. Each decision tree wants to create a node that is as pure as possible.
Pure, meaning all the samples in that node belong to the same class.
Exactly. You want 100% failure samples or 100% healthy samples. The Gini impurity function quantifies how messy or mixed up that node is.
Now, hearing that formula, G at irrelevant equals 1 sumber G to get as close to 0 as possible, right? Because 0 means perfect classification.
You nailed it. If G equals 0, the node is perfectly pure. The algorithm's job at every single split point is to choose the cut. For example, if pressure is greater than 150 psi, that maximizes the reduction in this impurity. We call that the gain or delta G geller.
So it's constantly striving to carve up the sensor data space into cleaner and cleaner little pockets until the leaf nodes are essentially pure classifications.
That's the whole game.
So beyond just the accuracy, a major strength of random forest in PHM is its interpretability. Why is this trust factor so crucial for the maintenance engineer who needs to move past a black box and, actually physically intervene on the machine?
It's everything, and it comes down to the feature importance score. Since the model is explicitly tracking how much each sensor feature contributed to reducing that Gini impurity across all the hundreds of trees, engineers get a direct readout of causation.
Oh, okay.
If a specific feature, like the skewness of the vibration signal, consistently leads to cleaner, more successful classification splits, it gets a high importance score.
Which gives us that critical, actionable rule. So if the RF model says, hey, this equipment is failing, the engineer can immediately look at the feature importance output and confirm that the model saw a pattern that corresponds to known physics. Something like rising temperature plus increasing vibration kurtosis points to early-stage bearing wear.
Yes. It links the data back to the physical reality of the machine. It builds trust. And this leads us to its unexpected dual role, a fantastic anomaly detection safety net.
Right, because random forest is primarily a classifier, but you're saying its ensemble structure naturally exposes truly unusual behavior, even points that were not technically labeled as an anomaly in the past.
It does. Think about it. How does a model that's trained only on known healthy and known failed states react when it sees something completely new, something that just doesn't fit the mold?
I would guess poorly.
It creates massive disagreement. Think about a normal sample. It tends to follow common high-traffic decision paths within all the trees. This leads to a strong consensus vote. Tree 1 says healthy, tree 2 says healthy, tree 500 says healthy.
But if a data point represents some bizarre pressure and temperature interaction that the model has never seen before?
Well, that anomaly doesn't fit those high-traffic paths. It might fall into a deep, rarely used branch in one tree, but a shallow path in another. Or it lands in leaf nodes that contain almost no training samples.
Ah, I see.
And because the trees were trained on slightly different subsets of data, they start to disagree wildly. Tree 1 says healthy, tree 2 says failure, tree 3 says degraded.
So the voting disagreement itself becomes the quantitative anomaly score. The more the individual trees argue amongst themselves, the more anomalous the data point must be.
Exactly. We can calculate the anomaly score based on 1 minus the normalized count of the majority class. If every tree agrees, the score is near 0. If the trees are fractured and disagreeing, the score approaches 1, indicating a highly anomalous data point.
So this makes random forest a crucial layer 2 safety net, even as a supervised model. It's ready to flag deviations that look like known faults, but it's also flagging points that just create internal chaos. We established that random forest is a great second line of defense for anomalies, but it fundamentally requires historical labels. I mean, we have to know what a fault looks like. But what about the true industrial challenge? A novel fault, an unexpected signal the supervised model has never seen, a zero-day incident.
And that's where we make the critical pivot to unsupervised methods, and specifically the isolation forest, or IF. The entire philosophical approach just shifts completely.
How so?
If random forest models normality so it can classify deviations, isolation forest doesn't even bother trying to define what normal looks like.
Okay, so it focuses purely on isolating the abnormality. Why is that approach inherently simpler, faster, and more robust for novelty detection?
Because anomalies are statistically rare by definition. They live in low-density regions of the data space. Imagine you plot all your sensor readings. The vast majority of normal operating points are going to cluster tightly together.
Right.
Any spike, burst, or unusual combination, that odd pressure, vibration, and temperature signature is naturally far away from that dense cluster.
So that isolation forest just exploits that distance. Anomalies are easy targets because they are, for lack of a better word, lonely.
Precisely. They are lonely outliers. We utilize what's called the short path principle. The algorithm builds many random trees called I-trees. And crucially, unlike the Gini-maximizing splits in random forest, these trees only pick a random feature and a random split value. And they just recursively partition the data until a single data point is isolated.
Wait, if the splits are entirely random, doesn't that make the model inherently unstable or inaccurate? How can we trust a prediction that's based purely on randomness?
That's the beauty of it, and it's why it's so incredibly fast. Since the goal is isolation, not purity, randomness is a feature, not a bug. If a point is deep inside a dense cluster of normal data, you have to split the space many, many times randomly to finally separate it from its neighbors. That results in a long path length through the trees.
So a long path means it's normal, dense data, and we get a low anomaly score.
Correct. And conversely, if the point is an outlier, an unusual pressure spike, or a massive shift in a wavelet feature, it often sits right on the edge of the operating envelope.
So it's easy to get to.
The algorithm can isolate it with just a few random cuts. That results in a short path length, which translates directly to a high anomaly score, often approaching 1.
That difference in philosophy seems fundamentally more robust for zero-day faults because it doesn't rely on any pre-existing knowledge of the failure mode. It only cares about what's happening outside the dense region of what is known to happen.
Exactly. It doesn't care what that outlier represents physically, just that it is an outlier. And this computational efficiency is its primary industrial strength. Isolation forest relies only on simple random splits and path length calculations, making it incredibly lightweight and fast to execute.
Which is why it's so highly recommended for edge systems.
Yes. For microcontrollers, PLCs, or edge gateways, where hardware resources are severely constrained, but the need for real-time monitoring of unexpected novel spikes is mandatory.
Okay, let's use a scenario. We're monitoring a cooling loop on a massive data center HVAC unit. Normal pressure is stable, let's say between 40 and 60 psi. Suddenly, a microfracture causes a momentary complex burst of pressure to 75 psi, coupled with a brief high-frequency vibration spike that lasts 50 milliseconds. Avast flags that instantly.
It flags the combination. That multivariate 0.75 psi high-frequency spike, short duration, sits far outside the dense operating density of normal.
I see.
Even if 75 psi alone isn't considered an absolute failure threshold, IF catches the novelty of the combination instantly before that event ever hits a supervised, labeled threshold.
So it provides immediate low-latency alerting right at the machine level before the data even has to be aggregated and sent back to the cloud for heavy deep learning analysis.
It is the necessary first layer of defense.
So isolation forest and random forest are fantastic at detecting a current fault or deviation. But as we mentioned at the top, the ultimate goal of predictive maintenance is prognostics, knowing how much life is left in the equipment, the remaining useful life, or RUL.
Right.
And that requires forecasting degradation trends, which demands a completely different mathematical approach. Deep learning networks designed for sequences.
We shift now entirely from classification and anomaly detection to regression and sequential forecasting. And the foundational tool for RUL prediction using these long multivariate time series sensor logs is the long short-term memory, or LSTM, network.
Okay, so why are traditional neural networks, or even basic recurrent neural networks, RNNs, useless for this task? Why do we need this specialized structure with memory?
Because degradation is slow and cumulative. Think of bearing wear. The subtle change in vibration characteristics from hour 1 is critically relevant to the signal change at hour 1000. Traditional RNNs suffer severely from something called the vanishing gradient problem. As they process long sequences of time, the information from the distant past, those early stages of wear, is mathematically diluted. It's effectively forgotten by the time the model processes the 1000th data point.
So if you need to track subtle bearing wear over months, traditional RNNs simply lose that long-term memory needed for an accurate cumulative wear estimate.
They're useless for it. And this is the problem the LSTM network solves. It gets around that forgetting of subtle early degradation signals over incredibly long time horizons.
So can you walk us through how it achieves this internal smart memory?
Absolutely. The LSTM cell is best visualized as a smart memory unit. It has an internal component called the cell state. You can think of it as math BFCT, which acts like a conveyor belt carrying long-term memory information across the entire sequence.
A conveyor belt? I like that.
And crucially, there are 3 distinct gates that control what information gets onto or off of that belt.
Okay, let's break down those gates intuitively, applying them to the PHM context. First up, the forget gate. What is it forgetting in an industrial monitoring setting?
The forget gate decides what information from the previous cell state should be discarded or forgotten. It outputs a vector of values between 0, which means forget completely, and 1, which means keep entirely.
Okay.
In a degradation context, if we had irrelevant high-frequency noise 50 time steps ago, or maybe a brief irrelevant power fluctuation, the forget gate learns to set those memory values close to 0. It ensures that only the meaningful cumulative wear pattern, the trend, is allowed to persist on that conveyor belt.
All right, so it's cleaning the slate. Next is the input gate, MathBFEA and MathBF-T, which controls what new information from the current sensor reading is written into that long-term memory.
That's right. The input gate decides what new information from the current sensor readings, MathBST, is important enough to update that long-term memory. So if the machine suddenly experiences a significant sustained rise in temperature, a key sign of increasing friction or lubrication failure, the input gate allows that new, meaningful information to be stored.
And if the input is just transient, meaningless fluctuation, the gate suppresses it, so it acts as a relevance filter.
A very smart relevance filter.
Or-
And finally, you have the output gate, which seems to be the one that turns all that accumulated memory into the final RUL prediction.
It is. The output gate determines which part of that cumulative long-term memory influences the network's current RUL prediction, or MathBHT. For example, early in the machine's life, the memory state might be mostly stable and unremarkable, so the output gate reveals a long RUL. But as the machine approaches the end of its life, the memory state is filled with severe wear indicators, and the output gate lets that critical information dominate the final estimate. It's essentially deciding, based on everything I've seen, what part of my history should I use to forecast the next time step?
That mechanism, the constant filtering, forgetting, and accumulation of subtle changes over time, is exactly what's required to track cumulative wear, whether it's early bearing damage or long-term component fatigue. The LSTM excels because it inherently tracks that temporal evolution across multivariate streams.
It fuses the entire history: vibration, pressure, speed, temperature, and load profiles, learning the complex time-based dynamics that govern the failure mode. A capability that simpler statistical models can't even begin to replicate.
But, and this is a big but, LSTMs have a speed problem. They have to process information sequentially, meaning they must wait for the previous calculation to finish before starting the next.
The sequential bottleneck.
Exactly. And that bottleneck led researchers to look for faster, parallelizable alternatives for real-time RUL prediction, which brings us to the modern deep learning showdown.
So we're moving past LSTMs, the classic foundation. The sources you shared make it clear that modern PHM requires alternatives that prioritize speed and efficiency without sacrificing that ability to track long-term dependencies. But before we even look at the specific models, we have to spend serious time on the core performance metric for this entire domain, the CMA-PSS score.
This is critical. It is absolutely critical because it tells us what matters most to industry: avoiding unexpected downtime.
Right. Standard error metrics like RMSE, root mean squared error, they treat all errors equally.
They do. If you predict a machine fails 20 hours too early, the RMSE is the same as if you predict it fails 20 hours too late. But in real-world logistics, the cost is fundamentally asymmetric.
Walk us through that real cost differential. Why is being late so much worse?
Okay, so predicting failure 20 hours early, what we call the safe side, is inconvenient. You lose 20 hours of valuable, useful life, but the maintenance is planned, the parts are stocked, and you pay standard labor rates.
But predicting failure 20 hours late, the dangerous side, is catastrophic. I mean, that means sudden, unexpected, unscheduled downtime.
And that involves a domino effect of costs, right? You have to immediately divert resources, potentially paying huge overtime or premium shipping costs for parts.
And you risk secondary damage.
You risk secondary damage. The failed part might destroy adjacent components, turning a minor bearing replacement into a major overhaul. And most critically, you interrupt production, which can cost hundreds of thousands or even millions of dollars an hour, depending on the facility.
The CMA-PSS score captures this reality.
It does. The CMAPS formula explicitly penalizes those dangerous late predictions exponentially harder to reflect that massive financial risk.
So the calculation uses an asymmetric penalty function. If the error is negative, so an early prediction, the penalty is mild. But if the error is positive, a late prediction, that penalty just skyrockets.
Precisely. The formula uses a smaller divisor in the exponent for late predictions, which causes the score to shoot up exponentially for every hour you are late. This metric forces the model developer to err on the side of caution.
That really clarifies the stakes. Okay, now let's look at the sources comparison table for RUL models using that synthetic compressor data. We have the GRU, the TCN, and the mighty transformer battling it out on these industrial metrics.
Let's start with the GRU, the gated recurrent unit. It's often seen as the simplified, faster-to-train sibling of the LSTM.
Right.
It consolidates the 3 gates of the LSTM into just 2, a reset gate and an update gate, which makes it highly efficient and reduces the parameter count by about a third compared to the full LSTM.
Yeah.
Is a solid, proven baseline for sequential data.
But according to the data, the clear winner, achieving the lowest RMSE, the lowest MAE, and the crucial lowest CMAPS score of 2,301.80 is the temporal convolutional network, or TCN. Why does the TCN dominate in this specific industrial comparison?
The TCN solves the LSTM's sequential bottleneck. LSTMs have to process time one step at a time. TCNs utilize convolutional layers, which can process long sequences of data simultaneously. They are highly parallelizable.
Oh, okay.
This structure allows them to be the fastest for inference in our comparison, clocking in at just 0.6535 milliseconds per sample, which is significantly faster than the GRU.
But wait, how does a TCN handle long-term memory if it's using convolutions, which traditionally only look at small windows?
That's a great question. It uses 2 crucial innovations, dilated convolutions and residual connections.
Okay.
Dilated convolutions skip inputs with a fixed step, which allows the network to have a massive receptive field. It can effectively look back hundreds or thousands of time steps to gauge context without adding significant computational layers.
And the residual connections.
Those help prevent the vanishing gradient problem, enabling deeper networks to train properly.
So we have the fastest inference time, the smallest model size with only 0.02 million parameters, and the best score on the high-stakes CMAPSS test. That combination points to a crystal-clear industrial recommendation, especially for hardware constraints.
Absolutely. For real-time systems and edge deployment where speed, low latency, and memory footprint are paramount, the TCN is the current undisputed champion. It offers the best balance of speed and predictive accuracy for high-throughput, constrained environments.
Then we have the transformer, the most famous architecture in deep learning today, yet in this specific comparison, it delivered the highest error, with an RMSE of 7.84 and the worst CMAP score of over 6,000.
I know, it seems counterintuitive.
It does. Why would anyone use a transformer if it performs so poorly here?
The quantitative weakness of the transformer in this test lies in its complexity and its inherent need for vast amounts of data. Transformers are notoriously data hungry. They have a dense internal structure with many parameters, twice that of the TCN in this test, that require massive labeled datasets to train effectively without overfitting. When data is limited, simpler models often win.
But what is its core strength that keeps researchers so interested in it for this application?
Their core strength is the attention mechanism. While LSTMs track memory sequentially, a transformer can instantly connect a degradation pattern from hour 5 to a critical event in hour 900, regardless of all the intermediate steps.
So it explicitly models the importance or attention between every single time step.
Exactly. So if you have a massive fleet of equipment, say 10,000 engines producing petabytes of run-to-failure data, the transformer's ability to maximize accuracy, reveal complex non-sequential pattern interactions, and provide superior interpretability via those attention weights makes it the research standard and the future target for highly complex, well-funded operations.
So the trade-off is perfectly clear. TCN for speed and operational reliability on constrained hardware, GRU for simplicity and a proven track record, and Transformer for maximizing accuracy and deep interpretation, but only if you have the massive scale of data and computational resources to back it up. We've covered the forecasting models, but let's transition to 2 other heavy hitters that serve critical, specialized roles in the PHM toolbox. First, the support vector machine, or SVM. In our deep learning world, SVM still holds a very important niche, fault classification, when dealing with what we call high-dimensional features.
It does. The classic application of SVM and PHM is binary classification, say differentiating normal versus mild wear, when your inputs are derived from intense signal processing. We're talking about features like the bins from a fast Fourier transform, or FFT of the vibration spectrum, or acoustic mel frequency septual
So
coefficients.
you could have hundreds of features for a single snapshot of time.
Hundreds easily. And why SVM thrives when presented with so many features, especially when we might only have small to medium datasets of labeled faults, is its mathematical elegance.
Which is captured by the kernel trick.
Exactly. Often, the features derived from complex signals, say acoustic features from a small crack in a gear tooth, are not linearly separable. They overlap visually in 2D or 3D space. The kernel trick, most often using the RBF kernel, maps that complex, messy data into an artificially much higher dimensional space where the points become clearly linearly separable.
That sounds incredibly abstract, mapping data into a high-dimensional space we can't even visualize. But the result is simple. A robust, nonlinear decision boundary is created without needing to explicitly compute that complex high-dimensional mapping, which saves massive computational cost.
It's highly efficient and elegant, and critically, SVM is sparse. Only the data points closest to that final decision boundary, the support vectors, influence the construction of the margin.
So all the other faraway data points are irrelevant to the final model definition.
Completely irrelevant. This makes the model inherently robust to general background sensor noise and effective even with smaller, precious labeled datasets, which are common in specialized acoustic gearwear diagnostics.
So SVM is the specialist tool of choice when the diagnosis relies heavily on sophisticated high-dimensional spectral or acoustic analysis rather than simple time domain metrics. Okay, now let's look at the best model for prioritization. Gradient boosting, often implemented via XGBoost or LightGBM. This is where we shift from when to how bad and which one first.
Right. Gradient boosting is arguably the strongest baseline for predicting failure probability and ranking assets by risk level. If your goal is not just RUL, but the urgent task of telling the plant manager, we have 20 compressor units, Unit 7 is 85% likely to fail within the next 30 days, while Unit 12 is only 15%, you need the probabilistic output of gradient boosting.
And how does this ensemble method manage to achieve such extreme accuracy, often beating deep learning models on pure tabular or feature-rich data?
It uses the principle of sequential correction. It starts with a very simple, weak prediction, often just the average failure rate of the fleet. Then, it builds many small decision trees sequentially.
Sequentially, okay.
And critically, each new tree doesn't try to predict the target itself. It tries to correct the residuals or the errors of the accumulated model built by all the previous trees.
So it's constantly improving its error rate by learning from the mistakes of the previous generation of trees. It's building a specialized tree just to fix the error gradient of the entire ensemble.
That's a perfect description. That sequential process, minimizing the gradient of the loss function, builds an incredibly accurate, finely tuned, and specific model. And implementations like XGBoost add further layers, using regularization to penalize overly complex trees.
And LightGBM takes it even further by optimizing the process for massive industrial data sets through what's called histogram-based splits, which speeds up training substantially.
It does, it's incredibly fast.
The sources emphasize interpretability here too. The visualization shows that the key features driving the failure risk in the synthetic compressor data are pressure VAR, pressure variance, and vibration arms.
And that's the link that makes gradient boosting essential for operational acceptance. Using SHAP analysis on the XGBoost or LightGBM model, the engineer can instantly verify which sensor feature contributed most to raising that failure probability score.
So if the model flags Unit 7 as high risk, SHAP can confirm that the increase is driven primarily by rising pressure variance and overall vibration RMS.
The engineer immediately knows where to investigate physically. It validates the high-accuracy data science with immediate domain expertise.
We've spent a lot of time on the glamorous deep learning algorithms and complex ensemble methods, but we need to talk about the brutal reality of industrial data. The expert consensus is just so clear. None of these models work if the data feeding them is garbage.
Not a chance.
The secret weapon in high-performing PHM is a meticulously designed, robust pre-processing layer.
Absolutely. Raw sensor data is the Wild West. It's noisy, it's scaled inconsistently, as you noted earlier. Pressure might run from 0 to 200, vibration from 0 to 20, and it contains high-frequency redundancy. A robust pre-processing layer is not an optional nice-to-have. It is mandatory.
This layer transforms the raw stream into the clean feature vector that the TCNs and gradient boosters can actually utilize effectively.
It does.
So let's start with the most basic necessity, normalization. Why do we need to force pressure and vibration into the same numerical landscape?
Because gradient-based algorithms, like deep neural networks, are highly sensitive to the numerical scale of their inputs. If pressure is 10 times larger numerically than vibration, changes in pressure will disproportionately dominate the model's calculation during the training process.
Regardless of whether that change is physically meaningful.
Correct. Normalization ensures all channels are treated fairly, typically using a text standard scalar to set the mean to 0 and standard deviation to 1, so that everything is operating on the same playing field. Without this, the model just learns to ignore features with smaller numerical ranges, even if they hold the critical fault information.
Once normalized, we deal with the ever-present problem of noise. What are the key industrial denoising techniques, moving from the simplest to the most advanced?
The simplest is the moving average filter for basic smoothing. It's fast, but it tends to blur sharp features, which we might need for fault detection.
Right.
A significant step up is the Savitsky-Golay filter. This is crucial because it fits a low-degree polynomial to a small window of data points. This allows it to smooth the data while still carefully preserving the important peak shapes and transient features.
So if you have a momentary impact fault, you need Savitsky-Golay to clean the signal without smearing that critical peak shape into oblivion.
Exactly. If the moving average is like smearing Vaseline over a high-resolution photo, the Savitsky-Golay filter is like Photoshop. It knows the difference between the noise grain and the important edges we want to keep intact.
That's a perfect analogy.
Mm-hmm.
And then we have the specialist tool for high-frequency data, particularly vibration analysis, wavelet denoising.
This is the ultimate expert. Wavelets are highly effective because they analyze the signal in both the time and frequency domains simultaneously. They decompose the signal into different scales, like looking at the signal under different magnifying glasses. Fault signatures, which are often short, high-energy impact bursts, appear very localized in both time and frequency in this wavelet decomposition. Noise, conversely, tends to be spread evenly across these domains.
So wavelet denoising can surgically remove the noise while keeping the important fault signatures.
Precisely. It uses techniques like the universal threshold estimator to identify and eliminate the noise coefficients while retaining the useful fault signatures, making the signal incredibly clean for downstream analysis.
So we've normalized and rigorously cleaned the signal. Now comes the moment where we turn the sheer volume of raw samples into concise information through feature extraction. We need to shift from raw samples, which might be 50,000 samples per second, to metrics that define the health state, maybe one metric every second.
Correct. We extract features across 3 fundamental domains. First, the time domain features. Simple statistical metrics like RMS, root mean square, kurtosis, skewness, max, and min.
Okay, let's quickly define those more obscure ones. When we talk about kurtosis, what are we trying to capture there?
Kurtosis is the measure of the spikiness or tailedness of the signal distribution. A normal, healthy machine signal has low kurtosis. As a crack or a bearing flaw develops, it creates brief, high-energy impact events that result in sharp, isolated peaks in the vibration signal.
So high kurtosis is an early warning sign.
It's often one of the earliest signs of a developing fatigue, crack, or bearing fault, long before the overall RMS vibration increases.
And skewness.
Skewness measures the asymmetry of the signal's probability distribution. A healthy signal should be symmetric, centered around 0. Changes in asymmetry can indicate specific mechanical issues, like rubbing or looseness.
Okay. Second, the frequency domain features, derived via the fast Fourier transform, or FFT.
These are absolutely essential for rotational machinery, where faults occur at specific, predictable frequencies. Things like 2 times rotational speed for imbalance, or specific ball pass frequencies for bearing faults. FFT features analyze the spectrum peaks and the power in specific frequency bins. This helps engineers isolate the mechanical source of the problem, verifying if the issue is a pump impeller or a motor bearing.
And finally, the most powerful, but often complex, wavelet features from the time-frequency domain.
Wavelet features are the gold standard for tracking transient faults. They capture the characteristics of a short, high-energy impact event like that sudden crack forming in both time and frequency simultaneously. They offer a level of diagnostic clarity that neither a simple RMS average nor a long-term spectrum can achieve alone.
After all this intensive extraction, we might have hundreds, maybe even 1,000 features per time window. We risk flooding the model with correlated or redundant information, which slows everything down and makes the model unstable. This is where the last step, dimensionality reduction, comes in, typically using PCA.
Right. PCA, or Principal Component Analysis, compresses the information without losing the most valuable variance. It identifies the directions in that high-dimensional feature space that explain the most variation in the data.
So you can boil it all down.
Exactly. By using PCA, we can take those hundreds of complex FFT and wavelet features and distill them down to 20 or 30 essential principal components. This significantly reduces redundant information, it reduces noise, and it dramatically improves the training speed of the downstream deep learning models.
Preparing that final, concentrated, clean feature vector ready for prediction. We've built a spectacular toolbox. Random forest for known faults, isolation forest for novel spikes, TCN for fast RUL forecasting, and XGBoost for risk ranking. Now, how does a leading industrial PHM engineering team fuse all of these specialized models into a single, multi-layered defense system?
The key to robust prognostics is layered defense, or fusion logic. No single model is perfect, and relying on one model's output, especially in high-stakes environments, is just a recipe for disaster.
Sure.
The gold standard runs 3 distinct layers in parallel, each specialized for a different type of failure signal.
Layer 1 is the immediate warning system, designed for speed and for catching the true unknowns.
That's the unsupervised layer, driven by isolation forest. This layer operates at the edge, listening constantly for sudden, rare events, critical outliers, and those zero-day faults that have never been labeled.
And because it's so lightweight.
It provides sub-millisecond warnings and alerts layer 2 and 3 that something unusual is happening right now.
Okay. Layer 2 handles the known subtle faults, the patterns we have historical data on.
That's the supervised layer, typically random forest or gradient boosting. This layer ingests that clean feature vector and confirms known fault signatures. For example, this is the vibration pattern of a stage 2 imbalance. And it also identifies those more subtle, feature-based anomalies through its voting disagreement mechanism, as we discussed earlier.
So it provides a classification of the machine's current health state.
It does.
And Layer 3 provides the crucial long-term outlook.
The temporal layer, powered by TCN, GRU, or LSTM. This is the forecasting engine. It ingests the historical sequence of clean feature vectors, tracks cumulative degradation over hundreds of hours, and outputs the critical RUL estimate. This layer gives us the time horizon necessary for proactive maintenance scheduling.
So the final step is the fusion logic, combining all these scores into a single, unified output that the plant manager can act on. How do you weigh these distinct model outputs?
Well, since the failure modes they are detecting are distinct and have different urgency levels, the output has to be a weighted average. The sources show a great example. You might take 0.4 times the isolation forest score, plus 0.3 times the random forest score, plus 0.3 times the LSTM score.
And the isolation forest gets the highest weight, 0.4, because a sudden critical spike is often a sign of imminent or catastrophic failure, demanding the fastest reaction time.
Exactly. The supervised model confirms the known fault, and the RUL model provides the long-term context.
The result is one clear, comprehensive text anomaly score and a continuously updated text RUL forecastifier. But we're back to the critical issue. The architecture is useless if the engineer can't translate those complex numbers back to a physical machine part. That's where the final piece of the puzzle, interpretability, comes in.
This is where S.H. Shapley Additive Explanations closes the loop and turns data science into engineering action. SJP takes the output of the final fusion score, or the RUL prediction, and breaks down the exact contribution of every single input feature to that prediction.
So the engineer receives the warning. Anomaly score is 0.8, RUL dropped 5 days overnight.
And immediately, SHA provides the detailed, verifiable answer. The RUL drop and high anomaly score were caused primarily by feature 57, which is wavelet energy in the third decomposition band on channel 2, and feature 12, increasing vibration kurtosis.
That link is gold. It translates the abstract model prediction directly back to a physical, verifiable change, like increased transient impacts consistent with a fatigue crack in the high-frequency range.
It enables proactive, targeted intervention rather than the engineer just blindly trusting a number. This entire pipeline, from sensor through pre-processing and 3 layers of defense to the final explain prediction, can be wrapped into a streaming function, fulfilling the true promise of modern predictive maintenance.
So what does this all mean for you, the learner, as you track these cutting-edge developments? We've moved far beyond simply knowing that AI predicts failure. We explored the precision of matching the exact mathematical tool to the failure mode. Isolation Forest is there for speed and for catching truly novel failures we never trained on. TCN is there to provide the most reliable, high-speed RUL forecast on constrained edge hardware, winning that CMPSS war by aggressively penalizing those financially catastrophic late predictions.
And we've reinforced the enduring value of robust preprocessing, turning messy signals into clean, information-rich features like kurtosis and wavelet metrics, and the essential nature of ensemble methods like gradient boosting for risk ranking and prioritization.
This entire sophisticated architecture is the mechanism that allows operators to move from reacting to catastrophic unscheduled shutdowns to proactively scheduling downtime weeks or even months in advance.
And that operational predictability is the difference between maintenance being an unavoidable cost center and becoming a massive competitive advantage.
Here's where it gets really interesting. It's something for you, the listener, to mull on and perhaps explore in your own professional context. We saw that the most sophisticated part of this entire system isn't the TCN or the LSTM math, but the interpretability provided by tools like SHAP. We can now precisely define which feature, be it text pressures, volume factor, or a specific wavelet coefficient, is statistically driving the failure prediction.
The provocative thought is this. As these prognostic systems become increasingly autonomous and highly accurate at flagging the precise statistical features that matter, how much does the domain engineer need to retain deep, complex knowledge of the underlying physical failure processes? Fluid dynamics, stress analysis, metallurgy.
Or do they simply need to trust the model's feature importance map and use their human expertise as the ultimate filter, verifying that the reason the model flagged the asset aligns with mechanical reality?
Is PHM becoming a discipline dominated by data science, or is domain expertise still the supreme arbiter of mechanical engineering?